Welcome, pre-calculus, to another round of the limits chapter. But today we're not going to be talking about computing limits. Instead, we're going to be talking about computational continuity. So, this is going to be a two-day problem set, so you're going to be asked to do a little bit more than a normal one-day thing, but it'll be due by the end of the week. We are approaching the end of remote learning. I only have like 2 more assignments that are like a week-long assignment length, so let's get to it. So, the directions say, describe the continuity of the following functions. Be sure to talk about removable and non-removable discontinuities. Note, the discontinuities are domain issues for the function. These discontinuities show up in most trig functions, even roots, and functions with asymptotes or graph breaks. All right, so it's kind of like saying, okay, we figured out with a graph of a function how to talk about its limits from the left, from the right, at that specific spot. Now we're saying, and then we moved on to what's the limit if we're talking about an equation-defined function. All right, so that's when you factored, you used the conjugates, you did all sorts of stuff. Now we are moving into, you know how to do continuity when it's a graph? Let's do the continuity thing when we're talking about the equation-based function. So, number 1. F of x is equal to 4 minus x squared over x squared plus x minus 2. Quick review of continuity. Specifically removable versus non-removable. Removable discontinuities were ones where the limit existed. All right, so that'd be like a hole in the graph. Yeah, pretty much like a hole in the graph. So if you go back, when we actually graphed rational functions that had holes in their graphs, you factor the top and the bottom, and you saw what factors canceled. The factors that cancel, those are holes in the graph. Those are removable discontinuities. So let's get to it. The top, is it factorable? Yes. It's a difference of squares. 2 minus x, 2 plus x. The bottom, is that factorable? Yes. In fact, I'm just going to pull a guess and check on this. Since it's x squared out to the front, then it has to be x times x. Since it's negative 2 at the tail end, you can only get negative 2 by taking 2 times a 1. The question is the 2 negative or is the 1 negative? Well, since the middle is plus, that means that the bigger number has to be plus in this case. So it's plus minus here. So here's what we have now. I'm going to try to get a marker that has more ink in it. All right, let's hope this guy can do the trick. X plus 2 and x plus 2 cancel. Oh, I like that. That means we have a removable discontinuity when x plus 2 equals 0. We have a removable discontinuity. I'm still using RD versus NRD. At x plus 2 when it equals 0. So it's not 2, it's negative 2 that creates the removable discontinuity. All right, so we got our first part. Now here's where a lot of students are kind of like, is that it? What's going on here? Well, the remaining function is a rational function that if we graphed it would have an asymptote at x equals 1, it would have a 0 at x equals 2, and it would have like a horizontal asymptote at negative 1. If you remember your rules for horizontal asymptotes, it's the ratio of the leading powers. All right, just a little review I just sprinkled in there. You like what I did there? Asymptotes are non-removable discontinuities. So you have a non-removable discontinuity at x equals 1, at x minus 1 equals 0. So when it says, describe the continuity of the following functions, I guess it's okay for you to just say it's non-removably discontinuous at x equals 1, and it's removably discontinuous at x equals 2. Continuous everywhere else. Yeah. So, if you express yourselves this way, I'm cool with that. Let's move on to number 2. By the way, I hope you guys are doing well. We've been extended to, what is it, the end of May? Stay-at-home orders? All right, hang in there. All right, I'm going to write this a little bit bigger so you guys can see it with me. As always, this is attached in Google Classroom. You should be viewing that as we move, if you can't see it on the YouTube video. All right, so the question is, do you know, or can you, factor the top and factor the bottom? Well, it looks like I can take an x out of the top. I'd be left with exactly 1 less power of x for each part. Additionally, I can take out an x from the bottom, leaving me with x and then 1 less x. Now, don't make the mistake of just erasing the x and saying that's all that's left on the bottom. You have to have a placeholder for factoring. So x times x is x squared. X times blank gives you negative x. Well, it's got to be negative 1. Okay? Now, since we still have a quadratic on the top, you ask yourself, is that quadratic factorable? The answer? It certainly is. X squared minus 4x plus 3 turns out to be x minus 3, x minus 1. I'm going to save you guys the nuts and bolts of how to factor a pretty basic polynomial like that because you guys have been doing it for a while. If you're struggling to factor polynomials, you're on your own for other YouTube videos. Was that too harsh? Nah, you guys aren't tissue paper. All right. So, now that we've factored the top and we've factored the bottom, x divided by x cancels out. That means we have a removable discontinuity when x equals 0. X minus 1s, they also cancel out, which means we have, again, a removable discontinuity at, I'm just going to kind of attach it to the other one, x equals 1. Okay. Now, nothing remains on the bottom, which means there's no asymptote to this function. In fact, if we were to graph this, it'd just be the line x minus 3 with a hole at x equals 0 and a hole at x equals 1. There are no non-removable discontinuities. All right, so I'm just going to maybe make a note here and say no non-removable discontinuities. And that's not a bad thing for you to do for your notes, to reference. Whoa. Discontinuity. Okay, got it. Just removable discontinuities at x equals 0 and x equals 1. All right. So, as long as you know how to factor, this looks like it's going okay. But what fresh challenge awaits us? All right, we have two separate fractions here. I will write them larger so that we can see it a wee bit better. Now, a lot of students, their natural inclination is to say, I see two fractions that are added together. I must find a common denominator. So they'll say, take negative 1 times x plus 5, x times 7x minus 3. They'll do a bunch of algebra, and then they'll be left with a polynomial on top and a polynomial on the bottom. and they don't know what to do. Lucky for you, you've got guidance here. If they're separate fractions like this, there's no need to combine them. You can just say, we have a problem with 7x minus 3. 7x minus 3 cannot equal 0. Yeah? Also, x plus 5 can't equal 0. Those are domain issues. In fact, they're asymptotes. So x cannot equal add 3 divided by 7, 3/7. X can also not equal negative 5. Those are places where the domain doesn't have an x listed, so to speak, right? There's no x value living there because there's an asymptote. So that creates a non-removable discontinuity at 3/7 and at negative 5. So it's non-removably discontinuous at x equals 3/7 and x equals negative 5. So that's not too terrifying. Number 4. Hey, look what we got here. Looks like a quadratic. We've been seeing those since Math 1. Let's see, quadratics are parabolas. In this case, it's got a leading coefficient of 3. Yeah, that means it's gonna be slightly stretched, maybe a little skinnier than normal, and it looks like this. Now, I'll save you guys the whole getting it in vertex form and graphing it as accurately as possible. Because polynomials, we know something about the domain of a polynomial. The domain is all reals. Okay, negative infinity to infinity, a polynomial lives a nice, happy, long life forever in one direction and forever in the other direction. So what does that say about continuity? It's continuous everywhere. And that's how you would respond. Describe the continuity. It's continuous everywhere. All right, we've got some, let's see here. 5 and 6, I want to do like an in-depth explanation, so I'm going to stop the video and then just start a new one on that. So be advised.